The kinematic equations are a series of equations used to predict and calculate different variables related to motion, including velocity, time, distance, and acceleration. These equations are partially derived from the relationships that we've observed between position and time. The kinematic equations are important because they're equations that allow us to predict and calculate motion. They derive from this relationship between position and time, derive from the relationship between velocity and time, and then derive from the relationship between acceleration and time. We'll be observing all of these relationships as we proceed through this course. Although we have not learned all these variables yet, the kinematic equations use all of them, so it's important to be familiar, especially as we learn and really get to understand these different variables related to motion. X is displacement. Remember, it's the distance between the initial and final position. A is acceleration. T is time. This is in seconds, always in seconds. B and V sub 0. These are very important. The final velocity is the velocity at the end of a scenario. The initial velocity is the velocity at the beginning of a scenario. So for example, if you were coming up to a stoplight, your final velocity would be 0. Your initial velocity would be more than 0. If a red light just turned green, your initial velocity would be 0. Your final velocity would be higher than 0 because you would be driving. Being familiar with the variables is very important, but being familiar with the units is even more important in many cases. Sometimes the unit is your only insight as to which variable you're looking at. It also helps us determine the new concept or the new variable we're analyzing when we're looking at the relationship between the independent and dependent variables in our lab. The unit for displacement, which we symbolize as x, is meters. The unit for acceleration, which we symbolize as a, is meters per second squared. So we measure acceleration in meters per second squared. We measure displacement in meters. Time we measure in seconds. Time we signify with the variable t, but we measure it in seconds. If you're given a unit of time other than seconds, for example minutes or hours, you need to turn it into seconds. If you're given minutes, multiply that value by 60 because there are 60 seconds for every minute. If you're given hours, multiply that value by 60 because there's 60 minutes in an hour, and then multiply it again because there's 60 seconds in a minute, and so forth and so on. We have two more variables, but they're represented by the same unit. V and V sub 0. Remember, V is the final velocity. It's the velocity the object ends at. V sub 0 is the initial velocity. It's the velocity the object begins at. They're different velocities at different time periods in the scenario, but they're both velocity. So they're both measured in meters per second. Our four kinematic equations utilize all of these variables in order to predict and calculate motion. There are four variables here. At this point, we won't be using all four, but it's important to see that they come as a set. This is a set of variables that you want to keep as a reference at all times during assignments, during assessments, during projects. No one would ever expect you to memorize these equations. Of the variables that are involved, if you look at each equation, one variable is left out. For our first equation, x, or displacement, is left out. For our second equation, v, so final velocity, is left out. For our third equation, t, or time, is left out. For our fourth equation, a, or acceleration, is left out. It's not included. We use this information of which variable is not included in each equation to determine which equation we need to use in each scenario. Selecting the proper kinematic equation for your scenario is very simple, especially if you have a kinematic equation derivation sheet that has not only the four basic kinematic equations, but has all of the equations derived for the individual variables. So you can worry more about the order of operations, less about solving for an independent variable. The first step in this process is to find the variable that is not included in your scenario. We will do this by looking at the given information, what we're being asked to find, and the variable that's left over is the variable that's not included. The second step would be to select the derived equation based on the variable you're solving for. So if you look at the variables below, we find the one that's all by itself. If I'm solving for v sub 0, if solving for t, etc. And you would choose the equation based on that. So let's try a couple. We have all of our variables listed out. We were given initial velocity, final velocity. We were given time. X is what we're looking for, so we're going to put a question mark by X. A is not included, so we're going to find the equation that is associated with A not being included. We're solving for X because X has a question mark by it, so we're going to use that equation right there. In this scenario, we were given both velocities and we were given displacement. We're being asked to solve for t, so A is not included. We find A is not included, and we're solving for t. So there's our formula. Instead of having to plug everything in and then go back and solve a multi-step equation, here you can just plug and chug, do a little order of operations. This process becomes one of 4 steps to solving a kinematic problem. Step 1. List your given variables, including the units to make sure they match up. Remember, a knowledge of variables and the units that they represent is very important. If I put down that x, or my displacement, is 5 seconds, a little red flag should pop up immediately and remind you that seconds goes with time. If you're looking for displacement, you need to find meters. It's a great way to organize and check that you are correct. A great way to be successful with step 1 is to list out all of your variables: displacement, acceleration, both final and initial velocity, as well as time. Step 2 is to figure out which variable the problem is asking you to solve and which variable is not included in order to select the correct kinematic equation. This is the process we just practiced. The variable that's not included will direct you to which of the 4 kinematic equations you need to use, and the variable that you're solving for, being asked to find, will direct you to which of the derived equations you need to use. Step 3. Once you've selected the correct kinematic equation, it's time to substitute the given values into the equation, plug and chug. This is straight up calculation time. The fourth and final step is to put the proper unit on the answer and to check if it's a reasonable answer. Reasonable can mean a lot of things. If you are doing a lab and you made a prediction that a velocity should be within a certain range, think about it. Is this too fast? Is this too slow? If your velocity, or whatever answer you're deriving, ends up being positive or negative have different meanings. Is it reasonable that this object is going backwards? Is it reasonable if this object's going forward? When you know you're dealing with constant velocity in kinematics, there's a couple of things that you should remember. Initial velocity and final velocity are the same. So v equals v sub 0. If you're told you're driving a constant velocity of 3 meters per second, you know that you start at 3 meters per second and end at 3 meters per second. It's like cruise control on your car. If you put cruise control on at 60 miles per hour, 10 minutes later you will end at 60 miles per hour. Velocity is a change in position over a time. Acceleration is a change in velocity over time. If we're dealing with a constant velocity, that means the velocity doesn't change. So our acceleration, or a, is always going to be 0 meters per second squared. This is not a value you would often include in a constant velocity kinematic equation. Most of the time we would see that acceleration is not included. However, in a situation, if you weren't given enough given information, you could substitute in 0 for acceleration. Let's take a look at an example problem. A man walks at a constant velocity of -4 meters per second for 3 seconds. How far did he travel? Which direction did he travel? Well, if he's at a constant velocity of -4 meters per second, that means he starts and ends with -4 meters per second. So that means my final velocity is -4, my initial velocity is -4. 3 seconds. The time was 3 seconds. Again, time is always in seconds. Take a moment during this first step where we're listing out our givens to double check that our variables match up with our units. Velocity is in meters per second. We're good there. Time is in seconds. We're good there. Step 2 of the process asks us to identify which variable is not included and which variable it's asking us for. This problem is asking us how far did he travel. How far is a measure of distance or displacement. So I'm going to put a question mark next to my x, next to my displacement variable. I'm trying to find how many meters he traveled. The only one that's left out is acceleration, which is not included. Again, with constant velocity problems, you'll see a lot of A is not included. So now let's select our proper equation. We start by looking at which variable is not included. A is not included, so that's going to bring us down to this equation. When you deal with constant velocity, you're going to see this equation a lot. We need to solve for x. So I'm going to find the equation that already has x by itself. That way I only have to plug and chug. I just have to do a little order of operations. When I find my proper equation, I'm going to write out the general formula of it. At this point, I need to have all 5 of my variables listed like I have to the left, and I have the general formula. Now I'm going to replace the variables that I know the given values of. I don't know x because I'm solving for x. It has a question mark next to it. I do know v sub 0. I know the initial velocity. I do know v, the final velocity. I do know t, the time. So I'm going to replace those values with values I know. V sub 0 is -4, v is -4, t is 3. It's all organized. Now I'm just going to do the order of operations, take care of those parentheses to give me -8. -8 times 1/2 gives me -4. -4 times +3 gives me -12. So my final step is to put a unit on the actual answer and ask if it's reasonable. Well, the unit is meters because I know that x is displacement. Displacement is measured in meters. Is it reasonable? I need to look at this scenario. A man's walking with a velocity of -4 meters per second for 3 seconds. Well, negative means backwards. He's walking backwards for 3 seconds. If he walks backwards 4 meters every 3 seconds, that's a total of 12 meters in a backwards direction. My final answer is -12 meters. Be careful to answer all questions on problems like this. We've answered how far did he travel. He traveled -12 meters. However, it also asks which direction did he travel. Now, those of you who are familiar with the positive and negative aspect of understanding our variables know that negative, just like a negative velocity would mean it's moving backwards, -12, negative displacement means we went 12 meters backwards. If it asks for that information, be sure to give that information.